Log on, tune in, find out. Another good idea from Cambridge.
Delivered by Professor Slava Melas from St. Petersburg State University from Russia. So, go ahead.
First of all, I would like to thank organizers for the nice opportunity to speak here. My talk will be about implementation of the functional approach to construction and studying optimal experimental design. First of all, I begin with short introduction, then more detailed explanation of the problem. The next chapter is about some condition for uniqueness of locally optimal design, and the main part is about functional approach, and I will conclude by numerical example to illustrate the main ideas. So the present talk is extension of my book and concern with studying optimal designs for nonlinear regression models. In particular, I will consider locally optimal and Bayesian efficient designs for nonlinear models under standard assumptions. For the full grounding, the approach requires some additional assumptions. The first assumption is that regression function depends on scalar variable belonging to the design interval. Certainly it is rather strong limitation, but it takes place in many practical models. The second requirement is that the function derivatives of the regression functions generate an extended Chebyshev system. It's not maybe not so known requirement, but in some papers it was proved that for many models these requirements take place. And what is more, the matrix of second derivatives of the optimality criterion by the different information matrix elements is positive definite. Usually in experimental design one use the first derivatives, but here we will consider the second derivatives, and if this requirement is slightly more stronger than usual requirement of convexity of the criterion. Certainly some further suppositions are needed, but they are rather simple, and then we can use that Jacobi matrix. This matrix is an important part of the approach I will talk about, is invertible. And this condition allows to apply the implicit function theorem for representing points and weights by Taylor series. And the results will be illustrated by example. Let me begin with some short introduction of commonly known things about experiential design, but maybe it's useful to review them. First of all, we will consider optimal design theory. For theoretical results, we refer to book Puck's scheme, and for more practical view, we refer to the book by Atkinson, Doneff, and Tobias. And in books and papers on optimal experiential design, it is assumed that design is just a discrete probability measure that give an external value to some functional of the information matrix. So I will follow this approach, and what is my goal? My goal is to provide some technology to construct and study these designs. In literature, usually two basic approaches are implemented. The first approach is finding explicit solution of external problem. Sometimes it concerns to reduction of the problem to some classical mathematical problems. As an example, we can point out to the optimal design for polynomial regression, where optimal points are the roots of well-known classical polynomials. So the problem of construction optimal design is reduced to some mathematical known problem. Another approach, which is more frequently used, is merely numerical construction. But both approaches have some limitations. Analytical approach is implemented only for rather simple models, and numerical approach does not allow to understand how sensitive the results to our assumptions. So we would like to consider another opportunity. Another opportunity is the so-called functional approach. The idea of this approach is to consider support points of optimal designs as functions of some parameters which are implicitly given by optimality condition. I will explain this in more detail in the following. And this function, in many cases, are real analytical and can be presented by Taylor series. This is not so unusual in other fields of mathematics. For example, when we calculate integrals, there is approach exact when we can calculate exactly integral, and then there is technique which is based on Taylor representation of integrals, and this is something similar, but maybe slightly more complicated, since here the criterion is very complex function. This approach was firstly introduced in my paper in 1978. There are a lot of papers when this approach was applied to linear as well as nonlinear problems, and they are collected in my book, but it was only locally optimal design and maximum efficient design in that book, and also it was considered some peculiar criterion, D criterion, E criterion, and C criteria, And now I will consider slightly more general case. And Bayesian design, which are the optimal, were considered in my paper with Staroselsky. So just it was a short review, and the present talk is about further development, and we will explain some sufficient conditions for a wider class of optimality criteria. So let us consider the standard nonlinear regression model with usual requirements on experimental errors. They are uncorrelated, unbiased, and with the same variance. And in many papers it is explained how we can extend results for more general case. I will not speak about this here, since it can be done in standard way. So we will consider the case when observation points are from a given interval, and as in many cases of practical interest, regression functions are given in explicit form. For example, well-known rational model is example of explicit representation of the function, but not linear. Usually, regression functions continually differentiable in the parameters, but we can suppose something more. We can suppose that regression functions are real analytical on the design interval. Real analytical, let me to remind that this means that the function can be represented by a convergent Taylor series. So under some further restriction which holds in the most of model, we will sorry. Okay. We will do. As usual, following Kiefer, we will consider this discrete probability measure as experimental design. This measure consists of support points and weight coefficients. It is usually called approximate design, but since we will not consider so-called exact design, we will not mention approximate every time. So if we like to consider real experiment, we should round weights to some weights multiplied by the general number of observations by some integers, and then we will have a real design for implementation. Let us consider least square estimator of the parameter vector. Under known condition, it can be proved that the vector, which is estimate minus true value multiplied by square root of total number of parameters, has a asymptotically normal distribution with zero mean and the following covariance matrix. So this matrix is our main object of investigation. And here the function are derivatives of the regression function by parameters. As about Bayesian approach, it was considered in many papers. Maybe one of the first one was published by Chelenach. And here we will consider Bayesian efficient design. What we can understand by Bayesian efficient design. We would like to minimize the following quantities. It's integral of ratio of determinant for locally optimal design to our determinant, and this ratio is integrated by some Prof measure. So this quantity shows how many times more measurements will be required if we will use our design in compare with locally optimal design for true value of parameters. But such a design can be constructed only by means of sequential approach. Such approach is not implemented in many cases, and in many cases it needs some additional work. So it's desirable to consider what is our loss if we use our design instead of truly locally optimal design, which can be obtained only by many series of experiments. Bayesian L-efficient design, L stands for linear, defined in the following way. Here we have ratio of two criteria, one criteria value for our design and another one for optimal design. And B is a given positive definite matrix. Using different metrics, we can provide designs with special ratio of precision of estimation for different parameters, which is useful for many applications, since the interest to different parameters is not equally strong. And Bayesian efficient designs were considered in some papers, but the functional approach was implemented in my work with Staroselsky, and here I will extend this approach to more general class of criterion, and this is the main purpose. Also, maybe not everybody know about that paper, and I will explain some basic ideas. The next topic is sufficient conditions for uniqueness of experimental design. It's close connected to functional approach and has some independent interest to understand under which condition the optimal design is unique. We can note that information matrix for nonlinear regression model coincide with the information matrix for linear model with fixed vector of parameters. So we can we can fix theta, and consideration of locally optimal design is the same as consideration of usual design for linear models. So this is only to stress that the results are interesting for linear model as well. So we will write f of x instead of f of x and theta, since theta will be fixed in this chapter, and so the problem is reduced to the design for linear regression model. Let us consider rather general criterion. We will call that design phi optimal if it minimizes the quantity phi of m of x, where m of x is information matrix and phi is some function. The usual requirement on this function is following. Phi is infinity if determinant is 0, phi continuous differentiable function, and more stronger condition that phi is a real analytic function. This condition is true for all known criteria, and some kind of requirement that if information matrix 1 is more than information matrix 2, then our criterion should be more. And also we will consider strictly convex function of information matrix. But in fact, we need the property that is slightly more stronger than the convex property, namely the matrix of second derivatives of the optimality criterion by the different information matrix elements is positive definite. This property can be proved for the class of Kiefer criteria, and it's slightly more strong than usual requirement. We collect this result in the following lemma. The functions listed here, determinant, trace, and Kiefer criteria, possess all the properties, and the proof is rather standard. I will not concentrate on it. Also, I would like to remember the generalization of Kiefer-Wolfowitz theorem, which can be found in Puckett's game paper book. So if the functions continuous linear independent on compact set, and if our criteria possess properties 2 and 4, then there exists at least one phi optimal design. The information matrices for all phi optimal design are the same. Any convex combination of optimal designs is an optimal design. And the following conditions is necessary and sufficient for optimality. So this is the main tool for deriving some properties. Let me remember some things about Chebyshev system. We will call continuous functions on the interval a Chebyshev system if the determinant is strictly positive for all distant points. And it is well known that at least one of the system, this one and minus this, since we consider the case when sign is not positive but strongly negative, and this is the requirement is that the linear combination has no more than k roots where coefficients are arbitrary real numbers not all equal to 0. Maybe is not so well known that system on functions can possess extended Chebyshev property. What does it mean? We will speak that some system is extended Chebyshev system if it is Chebyshev system and each function has continuous derivatives for the k, and any linear combination of this function has no more than k roots with a count of multiplicity. So in usual Chebyshev property, if two roots are coincide, the multiplicity is not taken into account. This definition is equivalent to that given in Karlin and Staten, but maybe it's not fully obvious since Staden in a remark to our paper with Holger first of all doubt that it is the same, but we convince him that this equivalent to his definition in terms of determinants. So we will have interest in systems that contain a constant function. I would like to pay attention to some constructive method for checking that the system of functions is an extended Chebyshev system. It's important since for complicated models used in practice, it's not easy to verify this property, but there is some general technique. Let us consider derivatives, then consider ratio derivatives, and so on. This construction is very simple, but I think that it's clear from the written version. So if the multiplication of all this function is strongly positive, then our functions form an extended Chebyshev system. I would like to explain some way of proving, since it's rather general and impressive. I didn't find it in the literature, but it seems me universal. Let us suppose that the linear combinations has more than k roots. That is, it has at least k plus 1 roots with a count of their multiplicity. It should not be so, and we will prove that this will lead to contradiction. It's well known that derivative of any continuous differential function has at least one root between any two roots of this function. Therefore, the derivative of our function has at least k roots. And I will not follow all details. Following these arguments, we can obtain that the function has at least one root, but this contradicts conditions of the lemma. Note that conditions of the lemma were used in the paper by Young published in Annals of Statistics for deriving some complex theorems on locally optimal designs. And Young did not notice that his conditions are in fact imply that the system is extended Chebyshev system, and this did not allow him to use the well-known properties of such systems, and we were able to generalize. Here we will use this property to derive sufficient conditions for the uniqueness of a locally optimal design. Let the functions be a Chebyshev system, and by this expression we denote a linear subspace generated by the functions. Theorem: let the functions phi sub 1 and phi sub m be continuous and linear independent, and let the criterion of optimality possess the properties from previous section. If for any indices the multiplication belongs to the linear space generated by k basic functions, then there exists a unique optimal design, and the further properties holds the design has m support points. This is coincide with the number of parameters, and at least one of them can coincide with the left boundary of the interval. And more general situation, we will need some further limitation, but all of them can be checked for many practically interesting models. So this theorem can be proved in the way very close to that used in our paper with data, and this theorem can be used to derive uniqueness of locally optimal design. Let us consider some example. Consider a rational model. Here we have a ratio of two polynomials, and we assume that denominator is not zero at the design interval, and the ratio is an irreducible fraction. Then we can introduce the functions psi from 0, psi from y, which are power functions multiplied by 4 degree of the denominator. And it's easy to calculate that multiplication of basic functions belongs to linear space, and if we assume that derivative is more than 2, then by our lemma the functions form Chebyshev system on AB. About this condition, we can refer to that yes, if this condition holds, then for any optimality criteria satisfying our conditions, there exists a unique optimal design for the rational model. The design has m support points, and two of the points coincide with the boundaries of the interval. This result was obtained by here at Alliance for d-optimal design. Here we have it for more general class of criteria, and as it was shown in our paper, the basic requirement fulfills if all the roots of the polynomial are real and outside the interval AB. So this condition can be usually easily to implement. Now let me go to functional approach. As it was mentioned, the idea consists in studying support points as implicit function. How we can do this? Let our design is of the following form. It consists of n support points and the corresponding weights. Then, due to necessary conditions for extreme point, we have that all derivatives of our function by x and by the weights are 0 for all support points that in the interior of the interval. For boundary points, this does not take place, and by this reason we should consider the structure, the number of boundary points and the number of inner points. And it's simple but important concept. Let us consider triple n sub 1 and n sub 2 and sub 3, where n sub 1 is the number of support points that coincide with the left boundary of the design interval, n sub 3 is the same number for right boundary, and n sub 2 is the number of support points inside the interval. This triple will be called type of design. So we can restrict attention to one of opportunity. We will consider the case when one point at the left bound, one point at the right bound, and other inside interval. The other cases are similar, and we obtain one-to-one correspondence between design and vector. Vector consists of support points which are inside the interval and all weights -1. So the problem of constructing optimal design reduced to the problem of optimization of function of several variables. We can introduce the function which depends on this vector and is equal to our criterion for information matrix calculated for the design with corresponding to this vector. This is derivatives and this collection of the derivatives. So we have the equation which guarantee optimality of design, and if the vector correspond to optimal design, then it's a solution of this equation. Let us forget for a moment about our definition and consider this function as arbitrary function of two variables. Then the famous implicit function theorem asserts that if this function is real analytic and Jacobi matrix is invertible, then in vicinity of corresponding point exists unique continuous vector function such that it's solution of the equation, and this function is real analytic. Moreover, we can write down explicit recurrent formulas for expansion of this function into Taylor series. And let us apply this theorem to studying locally optimal designs. Consider the following assumptions. Our function is real analytic. The criteria possess the standard properties. For any interesting parameter vector, there exists a unique optimal design of the following type. This is why we are interested in section 3, the problem of uniqueness. And the next condition is that the Jacobi matrix is a non-singular matrix for all the parameters. Consider the vector which corresponds to locally optimal design. Theorem asserts that this vector is a real analytic vector function of parameters if the assumptions hold. So the proof is based on the implicit function theorem in a way very similar to my book. As about assumption, first assumption, regression function is real analytic. We talk about this. It implies to many practically used regression models. Assumption 2, standard properties for the optimality criteria, holds for D criterion, L criterion, and Kiefer criterion. And assumption about type of the design is fulfilled if the condition of our theorem holds. So the conditions provided by section 3. And let us consider the last assumption, invertibility of the Jacobi matrix. The following theorem take place. Let the function formed an extended Chebyshev system, and optimality criterion is one of the following: determinant, trace, and Kiefer. And in this case, condition A4 holds. So this theorem secure our approach. And the proof, I would not like to go to details, but the proof is based on the representation of Jacobi matrix in the following form. This is matrix of second derivatives. It can be presented as sum of two matrices, and then we can verify that E is diagonal matrix and it is positive definite, non-negative definite, and to prove that this we will need only to prove that this matrix is positive definite. And for matrix B, it was proved in my book that it has full rank, and from lemma T2 say 2, it follows that the matrix Q is positive definite. So this is positive definite, and this completes the proof. It's very short sketch of proof. Note that rational regression function satisfy all assumptions. Another example is the following, and more examples can be found in the paper by Young. They are collected from different papers, but Young listed many interesting things. And now let us consider the problem of finding Bayesian optimal designs which minimize this quantity. Roughly speaking, this quantity is inversely proportional to Bayesian efficiency for optimal design. We can consider the following set. All parameters are between two boundaries, so vector C can be considered as approximation for true value, and Z can be considered as a relative error. And if we introduce uniform distribution on this set, then the problem is well defined. And we can follow as for locally optimal design. I would not like to list all details. And if we introduce notation for derivatives, then the following theorem. For some crucial value, there exists a unique continuous function such that the design corresponding to this function for fixed value of z is a Bayesian phi-efficient design for the distribution. This function is a real analytical function. The coefficient of this function can be recurrently calculated, and to consider the boundary point, we can use the following condition. It's just a version of equivalence theorem for Bayesian criterion. And if our design is Bayesian, then this equality can be true. So we can construct design for Z and verify for which Z this condition is true. And the technology is the following. We should find locally optimal design numerically or analytically, then calculate Taylor coefficients, and then check that the obtained design is optimal using theorem for 4. And the following numerical example. We consider rational regression function, and this function implies in some chemical industry, and we use the values from applied papers, and can check that our design has type 1, 2, 1, and we can find locally optimal design. So the first 4 coefficients of Taylor expansions of the functions shown in the following table, we see that coefficients are small. So if we calculate 4 coefficients, it's enough exact for all practical applications. and the corresponding design satisfies the condition of theorem 4 with such a precision. And the following figure show the relative efficiency of the locally optimal design with respect to Bayesian L-efficient design, and this is efficiency of the locally optimal design for the true value with respect to Bayesian L-efficient design. And for if relative error is not more than 50%, then the property of Bayesian design is close to locally optimal design, and this shows that locally optimal design is rather stable. So our results show that for considered model, locally optimal designs are rather close to Bayesian designs, not always, but if the relative error is no more than 50%. And let me give some concluding remarks. In this talk, it was shown that under some conditions that can be verified for many practically interesting models, locally optimal and Bayesian efficient design can be calculated by Taylor series, and the basic assumptions are regression functions depends on scalar variable and derivatives of the functions generate an extended Chebyshev system on the design interval. And the list of literature is here. Thank you.
Time for discussion, so if you have questions, please ask them. Anatoly?
It's not really my question, it's Luke's question.
No, it's my question.
It's okay, someone's question. So when you move from design to design, how can you guarantee that your weights don't become negative? So where is the mechanism which prevents weights to go below zero? Because you only
weights of the points.
Yes, for example. So where is the mechanism which prevents weights to become negative?
You see, we consider criteria which are comes to infinity if the design is not.
No, but you have many points, and one of the weights can go.
But here the number of points is equal to the number of parameters.
Ah.
Yeah.
So that sounds to the first question.
Yes, yes.
And
In fact, we can apply the approach to other cases, but we cannot guarantee that always Jacobi matrix will be invertible.
yeah.
But here we can guarantee it's the case.
And there was my question, which you basically answered already. Just because you're only using derivatives, and derivatives are local information,
Yes.
not global information. So
Yes.
when you're using derivatives, you can only trap to local extrema or go somewhere which you don't understand. Because, but probably because of the same reason, you don't your trajectories don't bifurcate, don't split in some critical points, and you are still following the path of true global optima. Because you always need to find global optima, right? What is optimal design? It's global optima of some bad function, right?
But in this case, we consider convex criteria. So the matrix
cannot be convex in X's and W's. It's convex in design, but not in these variables. It's very bad criteria.
No. The criteria is convex here. It's constructed in such a way that it is
It's
convex.
convex as a function of design, but you don't have design. You have weights and design points.
It is convex Yes.
Convex in weights, but not in axis.
Yes, it is not convex in axis, but here we use implicit function theorem. It's local theorem, but if the design is unique, then it becomes a global theorem.
Just because it's always unique for all your
Yes,
parameters, it's
yes,
all unique,
yes.
and you cannot split.
Yes, yes, exactly.
Any further questions?
Mhm.
Rainer?
Do you have any bounds on the efficiencies of your design? So if you go far away from the original point, your approximation becomes worse and worse.
You see, in the considerate model, if relative error is no more than critical value, then our design is enough close to optimal. So there is no problem. It's in fact it's practically coincide with optimal design. If in more general situation, it can be needed maybe next recalculation of Taylor series, not in one point. Taylor series calculated in some point. In almost all models which are considered, it was enough to construct one expansion, but sometimes it needs several expansions. So I can is here check. Oh. Mhm. So we have some point, and we have and when it's, begin some divergence, we can construct Taylor expansion from next point, and here next point. So by several expansions we can construct a representation for all the scope of the function where it is real analytic. If the function real analytic, it can be constructed by Taylor series as precise as desirable. Maybe not by one expansion, by several expansions. One, then next, then next. In the last paper, it will be illustrated.
Due to time constraints,
Okay.
I suggest to
Thank you.
wrap this discussion for now.
Okay.
Thank you very much once again.
Thank you.